So now that we have a good working definition of enthalpy, we're going to start using it in ways that seem relatively familiar, because this is the part of enthalpy that we studied last year. Enthalpies of reaction, or delta H, the change in enthalpy in a chemical reaction. And it's fairly straightforward. Anytime that we have delta anything, change in anything, it's always final minus initial. So in this case, if we're thinking of a chemical reaction, final is the enthalpy of the products, where initial is the enthalpy of the reactants. And you can see here in this diagram where on the left-hand side we have the reactants, which are oxygen gas and hydrogen gas. And then on the right-hand side we have the products, which is water. And the reactants are have a higher enthalpy than the products. So as the reaction proceeds from reactants to products, enthalpy is released. And you can see that the explosion and flames indicates that enthalpy was released into the surroundings. So the system lost energy, exothermic, and the surroundings gained energy. And so this delta H of reaction has a few properties. Number one is that it's an extensive property. This is a vocabulary term from first year chemistry. Extensive means that it depends upon how much there is. So something like mass and volume would be extensive, whereas like color and density would be intensive. It doesn't matter how much you have. So an enthalpy of a reaction sort of makes sense, that if I have just a few molecules of oxygen and hydrogen, it will release X amount of energy. And if I have many more molecules of oxygen and hydrogen, when they react, they will form way more energy. The enthalpy change for reaction is equal in magnitude but opposite sign to the delta H for the reverse reaction. And this again makes sense. We know that if it's, final minus initial, well, if I have the reverse reaction, the products become the reactants and the reactants become the products, then if I flip the whole reaction around, then I would be flipping around that final minus initial, and it would come up to be the same number, but just a different sign. And that's going to become especially useful when we discuss something called Hess's law. Number 3, the enthalpy change for reaction depends on the state of the reactants and products. So far, when we first introduced the idea of state symbols, H2O liquid versus H2O gas, we didn't really use it all that much. A little bit for when we were doing precipitate reactions and knowing which ones are solid or aqueous. In this case, when we're talking about the energy of the components of a reaction, it is going to make a difference because gaseous water is going to have a different amount of energy than liquid water. And that's going to factor into our delta H. So that'll become important in a few more sections. So relating delta H to a quantitative reactants and products. So how much heat is released, right? Circle the do. So it's looking for heat is released when 4.50 grams of methane gas is burned in a constant pressure system. And then this is the table that where we're going to get our information from. Where we're getting our information from, so it tells us that when CH4 is burned in oxygen gas, it will make CO2 and 2H2O. And we're sort of following the red arrow here because that's starting with CH4 and ending with CO2. So then delta H equals negative 890 kilojoules, which means when this reaction takes place, for every 1 mole of CH4, I forgot the 2 here. For every 2 moles of oxygen, for every 1 mole of carbon dioxide produced, and for every 2 moles of water produced, this system will release 890 kilojoules, right? That's what the negative sign means. It means it will release that much energy. So if that's how much energy is released for 1 mole of methane, we can just do a little stoichiometry, a little dimensional analysis to figure out what 4.5 grams of methane would be. So of course we start out by, underlining the clue, and it's 4.50 grams of methane. And then we use the molar mass of methane in order to convert this to moles. So 1 mole of CH4 is 16.042 grams of CH4. That's right from the periodic table. And then from the balanced chemical equation, 1 mole of CH4 will release 890 kilojoules of energy. So first of all, a very important thing is that this one is this one. So that if in the balanced chemical equation it was 2 or 3 or 4, the other side of the energy would need to be 2 or 3 or 4. But remember that the conversion factor for molar mass is always 1 mole. So that will always stay 1 mole. So now we plug this into our calculator, 4.50 divided by 16.042 times 890, and we get to 3 significant figures, 250 kilojoules. And if you're wondering, well, where did the sign go? I'm not so, it was negative here, and then when you put it in here, it was positive. So this is where it's really important to read the question. The question is asking how much heat is released. So the fact that they're already using the word released is telling you that they know it's going to be a negative number. They want how much. That number has to be greater than 0, right? How much heat is released has to be a positive number. If it said, what is the energy change? That's where they're allowing you to either put a negative sign or a positive sign, depending on whether the change was positive or negative. Okay, so it's just really important to read the question carefully at that point. Okay, there's a few more practice problems with this here. And with both of these practice problems, pause the video, try and give it a shot. This is what you did last year. So everyone did this last year in the stoichiometry unit chapter. It was during quarantine, so you may not remember it all that much, but you did it, I promise you. So the complete combustion of ethanol proceeds as follows. What is the enthalpy change for the combustion of 15 grams of ethanol? So this is exactly the same as it was before. They want the enthalpy change, which means that this could be negative or positive, and it's the combustion of 15 grams of ethanol. So I'm going to start with 15.0 grams of C2H5OH. 1 mole of ethanol is 46.0 grams, right? They tell you that in the problem. And then according to the balanced chemical equation, 1 mole will have an enthalpy change of negative 555 kilojoules. So now I need to do that out. Notice this is a multiple choice question. So could you do this without a calculator? Well, if you notice that 15 and 46, that's about 15 over 45. That's about a third. So really what I would want to do is look for what number is about a third of negative 555. That would be what I'd really be looking for. And 12 is way too little. It's not going to be 55 and it's not going to be 17. And I don't know what 422 is, but it's not 1/3. It might be 2/3, but it's not 1/3. And so I'm going to go with B. And if you plug it into a calculator, it does come out with about that answer. Right? So that's how you can do that problem without a calculator. And then practice exercise 2. This is another one. If you think you got this, pause this, try this on your own. This is how we would do it if we were teaching this in class. I would make you guys try this one on your own, and then we would go over the answer together. Hydrogen peroxide can decompose to water and oxygen by the following chemical reaction. Calculate the quantity of heat released. It's going to be a positive number when 5 grams of hydrogen peroxide decomposes at constant pressure. So I take my 5.00 grams, H2O2, convert it to moles. The molar mass is 34.016 grams. And, right, we need to use the coefficients here. So 2 moles of H2O2 will react and release 196 kilojoules. Plug this into my calculator. 3 significant figures, 14.4 kilojoules is the amount of energy that's released, the quantity of heat that's released. Okay, we're going to try a whole bunch of these for homework as well.